Professor Girvin. Thank you very, very much for doing this interview. It is my pleasure to host you on the podcast. I would like to begin with questions on quantum mechanics.
Okay.
What do you think, why people don't fully understand quantum mechanics?
Well, we start out as children living in basically a classical world dominated by friction.
Mm-hmm.
We don't really understand even classical mechanics, the world of free fall in outer space and frictionless gliding on an ice skating rink. Those were things that were unknown to Aristotle, and I think all children are sort of born completely understanding that when you stop pushing on something, it stops moving. And even classical mechanics is very, very hard to develop an intuition about. But you can see things. You can do experiments. You can see nearly frictionless ice skating rinks and so forth.
Yeah.
But in the quantum world, we just have zero everyday experience with it. We're dealing with atoms and electrons and things that you can't directly see without special instruments. And so in some ways, that's good because our senses can give us the wrong impression, even about classical physics. But it just means that, the quantum world is so strange. The behavior of particles acting like waves and waves acting like particles, without sort of direct experience, it's just very hard to comprehend how strange the universe actually is.
And there's also one wonderful sentence which says in quantum mechanics, you don't see what you get, but you get what you see.
Yes. The idea there is that one of the predictions of quantum mechanics is that even when you do exactly the same experiment many times in a row, you can get different results. You can get random results. And quantum mechanics is a kind of alternative theory of probability, really. It's not ordinarily probability. We resort to probability when we're ignorant of the details. Like I could have a box here and it could have a card in it, and that card has a value. It's a 6 or a 9 or a queen, but I don't know what it is because you gave it to me in a sealed box, but the card has a value. That's not true in quantum mechanics. There is no, there are no hidden variables that if we only knew about them, we could predict the outcome of the experiment. It's the act of you opening the box and measuring what state the atom is in or what card is in the box, so to speak, that brings that value into existence. That in classical mechanics, quantities, physical quantities, have values before you measure them. But in quantum mechanics, they do not.
Yeah.
And you can actually do experiments to show that they do not have values until you observe them.
I see. So how close do you think we are to building a quantum computer on a scale that it will help us solve problems which are unsolvable by classical computers?
Well, that's a question I get a lot and which is very difficult to answer. I want to be very careful in answering because there's far too much hype in the field now that quantum computers can sort of try all possibilities in parallel and tell you the answer immediately to any problem, and that's just not true. In fact, we don't fully understand yet all the power of quantum computers, and we know some types of problems that they will definitely be good for, and others they may be good, but we can't prove it one way or the other at the moment. So I would say, the technology is at a very early stage, very rudimentary, but we've made enormous progress in the last 20 years, and there are now companies producing devices with hundreds and even thousands of quantum bits, qubits. But we have a huge problem that the very thing that gives quantum computers their power over, superior for certain tasks to traditional or classical computers, is also their kind of Achilles heel. They're very, very sensitive to noise and perturbations from the environment. So right now, the quantum computers are getting bigger and bigger, but they still sort of forget their quantum information far too rapidly for us to be able to do useful computation. So I would guess, based on the rate of current progress, that this grand challenge, which is called quantum error correction, trying to make the computer be able to do long calculations without errors, based on the rate of progress there, I would say, in 5 to 10 years, they're going to be so much progress that it's starting to look to be of practical interest.
So would you say that superconducting qubits are a better choice for building a quantum computer than, let's say, trapped ions, topological qubits, photonics, and so on?
Well, so there are many different physical platforms, atoms, electrons, ions, artificial atoms made from superconducting circuits, which is what the team at Yale mostly works on. And it's far too soon to say which, if any, of these technologies will ultimately be the winner. Again, we're in a very, very early stage of these technologies. I would say that the leading contenders right now are the ones you mentioned: superconducting qubits, trapped ions, and neutral atoms that are held in little optical tweezers. And each one has particular strengths and weaknesses. Each one is making rapid progress, but we're still very, very far from the ultimate goal.
Yeah, I see. So how would you define the second quantum revolution?
Well, let's start with how we define the first quantum revolution. So, prior to about 1900, what we now call classical physics, invented by Newton and Galileo and others in later in the 19th century, was explaining many, many things, the orbits of the planets and, all kinds of things. But there were certain, cracks in the foundation that eventually led to the quantum theory beginning in 1900 and basically being completed by 1930, more or less. And this first revolution completely changed the way we think about the nature of reality, what is a measurement, probability and causality and so forth. And it led to the technological revolution of the 20th century. It led to the transistor, the laser, the atomic clock, which led to, you know, the internet and global positioning and computers and so forth. But all of those devices, you have to understand quantum mechanics in order to invent them, but you don't have to understand quantum mechanics to use them.
Exactly.
Quantum mechanics will predict for you what voltage it takes to turn on a transistor, which is a kind of switch. But you can give that device to electrical engineers and they really don't have to know any quantum mechanics in order to design computers and circuits and so forth. The second quantum revolution is based on newer ideas, not because the theory of quantum mechanics has changed. It's the same as it's been for nearly 100 years. But it's so strange and weird, and we have so little intuition about it, that we've only in the last 25 years come to appreciate that these quantum machines, like the transistor and the laser, do not harness the full power that's available to quantum machines. And they're not acting sort of fully quantum mechanically. And so in the last 25 years, we've come to understand that quantum machines can do much more. Our understanding of the information content of quantum systems has changed tremendously. Again, not because quantum mechanics has changed, just our understanding of quantum mechanics has improved. And so this new understanding is what's driving this second quantum revolution. We understand much better how measurements work, so we can now detect the tiniest imaginable signals, like quantum techniques are now used to detect gravitational waves, these ripples in space-time. And we understand the information content of quantum systems much better, and we're now able to build small quantum computers and quantum communication systems. So it's these new ideas that are driving this second quantum revolution.
Right, and now when we are talking about understanding quantum mechanics, what would you say, how does the Copenhagen interpretation of quantum mechanics differs from many worlds interpretation?
Well, now we're getting into
Tough questions.
a murky and difficult area. So the so-called Copenhagen interpretation of the quantum theory, which was put forth by Niels Bohr and his school of physics in Copenhagen, Denmark, says that something special happens when you make a measurement, when you observe a quantum system. There's a special rule that the quantum state collapses and gives you a random result that you sort of bring into being by this act of observing. And it's a little unsatisfactory because you think, well, the quantum theory, if it's correct, it should apply at all scales from electrons to people. And somehow the Copenhagen interpretation changes the rules once you get up to people scale or macroscopic scale. That seems unsatisfactory. But it's perfectly fine for doing calculations and you get the right answer. There's a different interpretation called the many worlds interpretation, which says that you know, this sort of randomness that you see is because at each instant the universe bifurcates into multiple possible universes, and that we are on one branch of this forking path, and that explains the random results. But there's no actual predictions of this theory that you can test. And in my view, it doesn't really satisfy Occam's razor. It's not very parsimonious of universes. It keeps creating new universes for which we have no apparent evidence. So it's also unsatisfactory from that point of view.
So you would say that we actually cannot prove or disapprove quantum interpretations, especially many worlds, experimentally.
I think that's right. The one, Feynman's school of thought on this was shut up and calculate. The quantum theory has some rules. If you follow those rules and do the calculations correctly, the theory will predict, make perfect predictions and it's been extremely well tested experimentally. No one disagrees on what the predictions are. It's only how you interpret them. And then there's all kinds of language problems and philosophical fights and which I don't think we know how to resolve.
I see. So in the many worlds interpretation, we have a universal wave function that never collapses. So how do you comment on that?
Well, so the idea there, I think, is that if the quantum theory is correct, then it should apply to everything, including you and me. And in some sense, that's fine. Let's say we do an experiment, and we do many tries, and each time it gives a random result. But in this picture of sort of the wave function of the universe, there are different possibilities encoded in that wave function. And there's an amplitude, what's called a quantum amplitude, that the meter that made the measurement reads 1, and our eyes see that it's 1. And there's another possibility, amplitude, that it reads 0, and our eyes are seeing 0. And there's a statistic, there's a perfect correlation between what our eyes see and therefore what we think the result is and that meter. But there's no, you can show from the what's called the linearity of quantum mechanics, the equations are all linear equations, that there's no way for a person to tell that they're in a superposition of the meter says 0, I think it's 0, and the meter says 1, and I think it's 1. I might be in a superposition of both of those things, but there is no way for me to tell that.
And what would you say, why was Einstein skeptical of quantum mechanics?
Well, this is very interesting, and it's kind of ironic because Einstein, really helped invent quantum theory. He invented the concept of the photon, the particle of light, had many important debates with Niels Bohr trying to understand the quantum theory. But in fact, he understood the quantum theory so well that he understood some of its strangest predictions. And this thing that he called spooky action at a distance, which we now call entanglement. He understood that so well, had such strange implications that he just felt that it had to be wrong. So in some sense, he had such a deep understanding that he became skeptical. What's ironic is that, when my experimental colleagues go into the lab every day to, do an experiment on a quantum computer, one of the first things they do to check that it's working is to do the experiment that Einstein said, the prediction of quantum theory could not possibly be right. And do that experiment, do the thing that Einstein said was impossible. And when it works, then you have a quantum computer and not a classical computer. So I think that's an interesting irony. And, it would be very interesting if Einstein were alive today to show him these experiments and where his ideas have led.
Is it true that maybe Einstein didn't like quantum mechanics because he didn't like probabilistic nature of quantum mechanics because he once said that God doesn't play dice?
Right. I mean, I think that was one of the things that bothered him, that previously in classical mechanics, if you knew the state of the universe, like where all the particles were and how fast they were going, in principle, not in practice, but in principle, you could calculate what's going to happen in the future. It's all deterministic. There's nothing actually random. And so it really bothered him that in quantum mechanics, you can prepare exactly the same experiment and get a different result.
Right.
That really bothered him.
Yeah.
But there's a play, I forget if it's by Tom Stoppard. Anyway, I've seen a clip from this play in which one of the characters says that the irony is, because Einstein helped invent quantum mechanics, it was Einstein who gave God the dice.
Yeah, that's a good statement. Okay, so what do you think about Feynman and his contributions to quantum mechanics and quantum computing?
So I never had the chance to meet Feynman or hear him speak. A number of my contemporaries certainly did, of course. But he was really an amazing physicist, and he had very novel and intuitive ways of thinking about quantum mechanics, and he invented a completely new formulation of quantum mechanics. There are three different sort of formulations of quantum mechanics that look completely different, but they're actually all different mathematical representations of the same idea. And his is called the path integral formulation. And he thought about, we think in classical physics of a particles just traveling in a straight line, or if there's gravity or something, or some force, they curve. But in Feynman's picture, that's just an approximation. You have to actually consider the particle taking all different paths from where it was launched to where it's detected. And those paths interfere in a certain way, just like waves do. So it's a kind of related to the wave-like picture.
Yeah.
And so he's incredibly famous for this this development. Many other things he did in particle physics, in condensed matter physics, his famous theory of superfluid helium and so forth. Then in the 1980s, he started thinking about very tiny machines, shrinking scales down to atomic level, and began to think about could you have a different kind of computing machine based on the rules of quantum mechanics? And he didn't really, he kind of had a kind of big visionary idea. I wouldn't say that he really, made a very specific proposal, but he had the idea that if you could control a quantum system, you could use it to solve the equations of quantum mechanics. That it would be a very natural thing to do, and we know that those are extremely hard to solve by modeling them on an ordinary computer. So he gets a lot of credit for that idea, and it triggered other people to, he's one of the early people to think along these lines, and it triggered really the thinking that led eventually to the second quantum revolution.
Yeah. So is quantum mechanics the best theory we have to describe the world around us and the universe?
So far, yes. I usually say that it's the best tested theory in all of physical science and really all of science. So there are certain predictions that have to do, for example, with an electron is like a little magnet. It has a certain magnetic moment and strength of the magnet. And using the theory of quantum electrodynamics, which is what Feynman helped invent, that value can be correctly predicted to many, I don't remember exactly, but around 10 decimal places.
Right.
And it turns out that if you try to modify the quantum theory, put in some small term in the equations, which would help resolve some of these paradoxes about, does quantum mechanics apply at macroscopic scales? Then it's very, very hard to do that. Something goes wrong with causality, or your predictions would start to disagree with experiment. No one has yet found any way to modify the quantum theory. And so far, it's passed all possible tests. I mean, of course, we can't predict everything because the equations, while deceptively simple, are actually, not easy to solve except in simple circumstances. But in those cases where we have been able to solve them for simple things like an individual electron and so forth, the predictions have been extremely accurate, essentially perfect as far as we can tell.
Okay, so does the probabilistic nature of quantum mechanics imply that our reality is actually probabilistic rather than deterministic?
So that, yeah, I don't know. We certainly feel that it's probabilistic because we can do experiments and prepare things in exactly the same way, not just approximately, but exactly, and get what appear to be completely random results. So it certainly appears that there are quantum jumps. There are just, when you observe a system, it can suddenly change its state. For example, an atom in an excited energy state can emit a photon, and the electron falls from a high energy orbit to a low energy. Suddenly, we see all of these apparently non-deterministic, probabilistic jumps. So it certainly feels not smooth and so forth. But even our understanding of these so-called quantum jump processes has also changed in recent years, in part based on experiments here at Yale.
What does quantum mechanics says about consciousness? Can consciousness play a role in the collapse of the wave function? Or is consciousness itself a quantum phenomenon?
Well, this is a topic that some people have thought about. I haven't thought seriously about it.
Yeah.
You know, consciousness is something we don't really understand, I guess. At least I don't.
Yeah.
And so some people have thought, well, maybe, there are questions around free will, for example, do I actually have free will, or is my decision to do something the caused by some quantum fluctuation in my brain, or so forth. And at this point in time, we have no serious reason or evidence to suggest that like the human brain is really different than other macroscopic objects, which are very well explained by the laws of classical dynamics.
Right. So what would you say, how does quantum entanglement affect our understanding of space and time?
Well, I think that's not quite the right statement. So there are two things. This is related to this Einstein-Podolsky-Rosen paradox, which is the thing that Einstein was really worried about as a prediction of the quantum theory, this spooky action of distance. And there's two aspects of the quantum theory. You can talk about locality and you can talk about realism. So it appears in our description of certain experiments that unentangled particles, which have been separated by a large distance, that the measurement by one person of the state of one of the particles suddenly collapses the state of the other. That's true in sort of, if you follow the rules of quantum mechanics for what happens when you make a measurement, the quantum state of the other particle changes, or the state of the particles both changes suddenly. But it turns out there's no measurement the other person can do to tell that anything happened. In fact, their results are still random. The only way they can find out that something interesting happened is if they communicate with each other to compare their results. And that always takes place below the speed of light by the principles of relativity. So it's the recipe that we use to do calculations says the wave function, or the state, changes instantaneously across a large distance. But that's kind of like a crutch for how we do calculations and make predictions. The actual predictions, there's nothing predicted that anyone can see in experiment. In fact, you can't tell the difference between, if you have two people, Alice and Bob, each with a qubit, neither one can tell who measured first, for example. So if you carefully phrase what's actually happening and what's actually observable, it's the so-called locality is not being violated, that you don't have cause and effect instantly, transmitted. What what quantum mechanics doesn't have is realism. That is, there isn't some hidden variable that tells you what the result is going to be. If only you could measure that. It just isn't there. And it's, again, this example that you, by the act of measuring, you bring into existence the value of certain quantities.
I see. What role does information play in quantum mechanics? How fundamental is information in description of quantum system?
Yeah, so I think, as I mentioned previously, the second quantum revolution is really coming about because we now understand much better the role of information in quantum systems. And you can cast the fundamental equation, the Schrodinger equation of quantum mechanics, how quantum states evolve in time, as representing a conservation law. We have conservation of energy, conservation of momentum, and so forth. You can cast this fundamental law of how states evolve in time as conservation of energy, of information, sorry. And, technically it's called unitary evolution, and that actually, the way to describe that is through conservation of information.
Right. So how can we interpret the wave function? Can we say that it is a real physical entity or just a mathematical tool?
Well, I think in the example we just talked about with the apparent spooky action at a distance, it's our description. The wave function is our description of the state which we use to make predictions. And that apparently changes in some unphysical way, sort of instantaneously across the universe. But it doesn't have any physical instantaneous consequences. So some people feel that the wave function is just a useful mathematical tool, but it gives us a false impression of what's going on, although using it, we always calculate and get the right answer. So it's, I think before I came to think about entanglement and spooky action at a distance, I might have said, oh, it's just, the wave function is a real thing and we use it to calculate. But after, this so-called Bell inequality picture of the Einstein's puzzle, I have to lean a little bit toward it just being a mathematical crutch that we use to do calculations.
Yeah. What is your standpoint on the theory of everything? So basically how to unify general relativity and quantum mechanics. So would you say that maybe string theory or quantum gravity are the best tools to do that?
Well, this is a little bit beyond my own expertise, but I wanted to actually bring this up earlier when I said that the quantum theory was the best tested, most precise theory we've ever invented in any field of science. But we know from just sort of general arguments that the quantum theory and Einstein's theory of gravity, the general theory of relativity, are mathematically inconsistent with each other. So each has to be an approximation. And string theory was developed in the hope of producing a theory that had both quantum mechanics and gravity in it, and it succeeded, but there haven't been a lot of sort of useful experimental predictions. There's been some improved understanding of what's called the black hole information
Yeah.
paradox, but string theory hasn't sort of produced a unique theory. There are too many possible string theories. So quantum mechanics, you want to combine that with gravity. So gravity in Einstein's picture is caused by the fabric of space and time being somehow curved and distorted. And in quantum mechanics, a particle can have an amplitude to be here and to be over here. But if that particle is producing a gravitational field, then it's warping space-time in one way if it's here and another way if it's there. So now I need a quantum superposition of different space-times. And now things get confusing because time itself is a essential parameter in quantum mechanics. I mentioned earlier the time evolution of a state is based on conservation of energy. But now, in gravity, time seems to flow at different rates in different parts of the gravitational potential. It all gets very, very, very confusing. And there isn't really, this mathematical problem of trying to combine these is not a serious problem until you get to incredibly high energy scales, the so-called Planck scale, which we will never reach with any particle accelerator. So it's more a problem of principle than practice. But yet, it's a fundamental problem. So people are struggling with this. They're trying out different kinds of string theory. They're thinking about black holes. Now we're starting to measure mergers of black holes. So, we may eventually get some kind of additional insights from experiment on how to combine gravity and quantum mechanics. But right now, it's one of the great unsolved problems of physics.
Right. You also work in quantum communication. So how can we achieve secure quantum secure communication in a quantum world?
Well, this is very interesting. So one of the, exciting developments that triggered the second quantum revolution was Peter Shor's algorithm for factoring large numbers into their prime factors. And the whole basis of public key encryption on the internet is based on the mathematical difficulty of doing that, but the ease with which you can check if someone claims that they've factored it, that you can check whether they're right or not. And this so-called one-way problems can be used to create encryption algorithms. And Shor's algorithm, he showed that a quantum computer, if you could build a large, very large, perfectly working one, could find these prime factors of large numbers very exponentially faster than any known classical algorithm. So it looked like privacy was losing out. But we now understand that actually in the end, in the battle between offense and defense in the cryptography world, that actually privacy wins out. So you can do quantum communication by sending quantum bits, for example, photons that have a vertical and horizontal or in-between polarization, can be transmitted in such a way that even an adversary with a quantum computer cannot break cannot eavesdrop on your communications and decipher them. So it's the security of the current internet protocols is based on the difficulty of solving some math problem on a large classical computer. The security of quantum communication is based on the laws of quantum mechanics, that if there were an eavesdropper who tried to take a look at the bits that were being sent, their values would randomly change.
Yeah.
And there's a protocol by which you can detect the presence of this eavesdropper. So in the end, the second quantum revolution will actually bring enhanced privacy.
Right. So how would you explain what circuit quantum electrodynamics is to a complete layman?
Well, let's start with electrodynamics. So that's the theory that sort of unifies the quantum theory and Maxwell's theory of electricity and magnetism, the theory that explains light waves and heat and so forth. And as I mentioned, people thinking about how an individual electron can emit and absorb photons, particles of light, that allowed physicists to make these incredibly precise predictions of the quantum theory, and were verified by experiment. So beginning about 25 years ago, we started applying these ideas of individual electrons and atoms talking to photons to not natural atoms, but synthetic atoms built out of superconducting electrical circuits, and not talking to visible photons, but to microwave photons. So they have much longer wavelengths, sort of centimeter scale. They have frequencies which are much lower than optical visible photons. They're about the same as your cell phone uses. And so we kind of developed a theory of the quantum mechanics of these microwave electrical circuits. And, my experimental colleagues, Rob Sholkoff and Michel Devereux, did all these amazing experiments where they could see that microwaves, despite their name, are particles, and there are individual photons that are just as good photons as the ones that, trigger your optic nerve. And it led to, it was kind of built on ideas from the optics community in what's called cavity quantum electrodynamics, where you put mirrors to give the photons many chances to bounce back and forth and interact with the atoms. And it was we kind of stole those ideas and moved them down to electrical circuits. And it's been amazing to see this idea, spread through the community, and it sort of forms now the industrial standard architecture for building quantum computers out of superconducting electrical circuits operating at microwave frequencies. And it's been amazing to watch all this development.
Yeah. Do you think that atomic clocks will replace classical clocks in some future?
Well, I mean, many, the clocks, the ordinary clocks that are plugged into your 60-cycle outlet, they don't keep perfect time, but at any given moment, they can be off by a number of cycles. But all the electrical generators in the United States are synced together using atomic clocks, and that's why your wall clock doesn't actually drift unless the power goes off. we use small atomic clocks in the electronics racks that control the frequency of the microwave signals that we use to operate quantum computers. So, they're everywhere. And, of course, they're in the GPS satellites, which tell your cell phone where you are and so forth. But even small ones are, too large to carry on your wrists. So, but you can get atomic clock time signals through your cell tower because that's how they tell where your phone is and so forth.
Yes.
So I'm not sure, they're not going to replace your wristwatch, but your wristwatch is going to know what time it is because of atomic clocks.
I see. And I only have 2 more questions.
Sure.
What would you say was the biggest technological innovation of the 20th century?
Well, I mean, you have to say it's either the transistor, the laser, or the atomic clock, I think.
Yeah.
The transistor probably wins. So, the first transistor was built in 1947, I think.
Okay.
At Bell Labs, and it was almost a centimeter on a side and had wires sticking out of it, and there were solder blobs, and it looked very, just homemade, crude thing, but it worked. And those, the people who invented the quantum theory did not, they were just thinking about the nature of reality and why atoms seem to glow different colors and so forth. But these more practical people who invented the transistor, used the quantum theory to invent the transistor. But even though they were more practical people, they could not foresee what their invention was going to lead to. So today, in every second of every day, there's more than 20 trillion transistors made each second.
Wow.
Fortunately, they're very small.
Yeah.
But that's a scale up and an impact which is just impossible to imagine anything bigger.
I see. And the final question, what do you think about artificial intelligence and the impact it will have on the humanity?
Well, again, just because I'm an expert in quantum mechanics doesn't mean I know what's the answer to that question, but it's certainly a very interesting question. And the fact that people are now able to build special purpose computers that have these neural networks inside them, or the things that imitate the dynamics of the neural circuits in your brain, and can be programmed at great energy and environmental cost, actually, to apparently, recognize patterns and do things that some of the tasks that people seem to be able to do is amazing. We don't yet understand where this is going, I would say, at least I don't. It's still a kind of crude technology, it hallucinates, it gives you wrong answers, it gives you nonsensical answers sometimes. But you could imagine that this technology is going to, at a minimum, eliminate a lot of routine work that people have to do by just, capturing all of that, and you can instead of programming a computer, you can give a general English language or whatever your favorite native language is, description of a task, and it will, with a little feedback, correctly start, producing the desired program results. But again, there's a lot of hype, much like in quantum computing, but there's no doubt that some enormous change is now underway, and it'll be interesting to see where it goes. Let's just hope it's not too interesting.
Do you think it will surpass quantum mechanics or quantum computing in the long term in terms of the impact on our lives?
Well, certainly. I mean, again, I don't know the answer, but it's artificial intelligence is going to take longer than some people think in order to become reliable and have this major practical impact. But and people have been working on this since the 1950s. So, and there were many winters and periods where it wasn't working and so forth.
Exactly.
So the same will probably be true for quantum. I would say the near-term impact will be larger for artificial intelligence than quantum, but the long-term, it's hard to say.
Professor Girvin, thank you very much for this conversation. I really enjoyed it, and you are truly one of the experts in the quantum mechanics, and it was my great pleasure to host you on the podcast.
Well, thank you very much. It's been fun chatting.
Thank you so much.
Pleasure.